This afternoon. So we'll have 3 talks. First, Judith Rousseau on something with ABC posteriors. Then we have Andreas Elsener, and then there will be Rajan Shah on XYZ algorithms. So we cover the whole alphabet. So I think Judith is very well known. She gave IMS medallion lecture recently. She just moved to Oxford. And maybe something that you don't know is that she actually shares her birthday with Jonas Peters and myself.
Oh wow, yes. It's not this week.
Yes. So Judith, please go ahead.
Thank you. Thanks for the introduction. Thanks for the organizers for inviting me. It's a real pleasure to be here. So I'm going to talk about some joint work I did with David Frazier and Gail Martin, who are in Australia, and Christian Robert, who is in Paris, whom you probably all know. And it's about an algorithm which is called ABC, and I'll first describe what the algorithm means and first notations. So you have data y, and it's going to be yn because there is asymptotic story here. That depends on some parameter theta, and here theta is finite dimensional. So I'm not going to be in a high dimensional theta. It's going to be high dimensional latent variables, typically. And that so you put a prior pi, so pi is a prior, and you get the posterior distribution. So your pi is a density with respect to some measure. And so then you have the posterior density, which is proportional to the likelihood times the prior. And the aim of the game is to sample from this guy. Okay, so you want to sample from the posterior distribution, P of theta given y. And so, but you are in a context where the likelihood is intractable, so you cannot compute the likelihood. You cannot analytically compute the likelihood, or you cannot even use Gibbs sampling to compute the likelihood, because typically you would have, like, for instance, a huge dimensional latent variable, like trees or something like that. And sort of the origin of these algorithms were in population genetics, where the U is so complex that actually sampling U given theta and then in the algorithm is too time consuming, so you cannot do that. And so another situation is when, for instance, the likelihood depends on the normalizing constants which you cannot compute, and then so you cannot compute this f of y given theta, and so you cannot do the usual story to do MCMC and that sort of things. So it's a technique that's sort of recent. It will look very naive, but in some cases, sort of that's all you can do, more or less. So the idea of the algorithm was, the first version was from Tavare in '97, so it's not that recent. So that's, and it's very basic. So what you do is you sample the theta, for each iteration you sample a theta from the prior, then you sample new data, you're using this new value of the theta, so from f theta prime, and then if the data that you have sampled is exactly equal to your observation, then you accept the new data. And if it's not, then you go back to here. So you sample a new data from the prior z from f theta prime, and you check whether they are equal or not. And if you do that, what's sort of interesting is that the thetas that you have kept are sampled from the posterior distribution. So it's a very simple proof, because what you know is that the posterior distribution is so the result of the algorithm is has a density which is proportional to this object. And here, because you accept only if z is equal to y, f of z given theta, the likelihood is f of y given theta I, and that's exactly the posterior distribution. So that's a 2-line proof, so it's very simple. The problem here is that you need to have equality, z equals y, and if z is high dimensional, even if discrete but very large, then z equals y becomes an extremely rare event, so you never see that. And so you're going to do something approximate to do that, and if z is continuous, then you never see that. So it's a lost story. And there will be 2 levels of approximation, essentially. So the approximate Bayesian computation, A for ABC is approximate Bayesian computation. Algorithm starts the same. So you sample from the prior, and then you generate new data from using the new parameter that you have sampled. And then you're going to accept what you've generated, not if z equals y, but if the distance of between z is some metric between z and y is less than epsilon. But it's not exactly the metric between z and y, because if you were taking the distance between z and y are like n dimensional vectors, and n is 10 millions, again, is going to be too restrictive, and so you never see something like that if epsilon is not too small, is not too large. And so what you do is you take a summary statistic of your data, eta of z, and what you're going to look is at the distance between the summary statistic, eta of z, with the observed summary statistic. And if this is small, then, and so you fix the threshold epsilon here. If this is small, then you accept your new data, your parameter, and if not, then you start again. Okay? And so you have two levels of approximations here. One is the epsilon, and the second is the fact that you're not looking at the whole data, but you're looking at the summary of the data. And then, of course, the question is, how do you choose the summaries of the data, and how do you choose epsilon? And there is a trade-off, because I'm just checking. Yeah, I'll talk about the trade-off just in 2 slides. So if you do that, then what you're simulating 2 things, theta and theta, and so you have a joint posterior density, approximate posterior density, which is equal to the prior times the likelihood at z times the indicatrix of this set for which when you have accepted, which means that the distance between eta z and eta y is less than epsilon, divided by the normalizing constant. Okay, so this is not exactly. So what you're looking at is an object which is not going to give you the exact posterior, but something else. So what you're interested about is this object, which is a posterior distribution, which is the integral of the likelihood times the prior over the normalizing constant. But here what you're considering is the integral of this probability of accepting times the prior divided by the normalizing constant. So you're looking at an approximated object of these things. And if you think about it, you can really think about this approximation, what it means. And so the generic idea here is that if epsilon was 0 or went to 0, this I have to assume that the dimension here is 1, but otherwise you take another normalization. Then the probability of this acceptance set divided by a normalizing epsilon is sort of equivalent to looking at the density of the summary statistic given theta. And so somehow what you're looking at is not if epsilon were equal to 0, you wouldn't look at the posterior distribution of theta given y, but the posterior distribution of theta given eta of y. So if epsilon were equal to 0, then that's sort of the best you could do, the posterior distribution of theta given eta of y. So if eta of y is a sufficient statistic, then you are happy because you're recovering what you want, if epsilon were equal to 0. But here epsilon is not equal to 0, so you're not having that. And also, in most cases, you don't have a sufficient statistic. So you just have a summary statistic that's not sufficient. So you're losing information in going from y to eta of y, and you're losing information from going to epsilon equals 0 to epsilon, which is strictly positive. And so there is a trade-off between the dimension of your summary statistic, because if you have a high dimensional summary statistic, then this set is going to be very constrained, and the probability of accepting the event is going to be very small. And so you'll have to do a lot of simulations to actually accept a few thetas. And so, but if eta z is a very small dimensional, then you tend to accept a lot of time, but you will have lost a lot of information from the data. And so you want to find a good eta z such that you don't lose too much information, but in the same time it's not too high dimensional, because otherwise you'll never accept what your algorithm, and it's going to be very inefficient. But it's approximate, so we're not recovering the true posterior, but we're recovering this sort of ABC posterior. Okay. And so now we take an asymptotic point of view, and the asymptotic is saying that we have some information in our sample. The information in the sample is going to increase, and because we've been clever, hopefully, we have summary statistics that are teaching us something about the parameter, and so they are going to concentrate. And so that's all we're going to assume. We're going to assume that as the information in the sample increases, whatever the information in the sample means, there will be a concentration of our summary statistics around some quantity that depends on the parameter, and that's going to allow us to learn for theta. If you take a summary statistic that doesn't concentrate, then you're not learning anything, and so there is no point with the summary statistic. That's sort of the idea, and so you want to have summary statistics that teach you something, so that, in other words, they are concentrated on some information. And that's how we formalize it, essentially. And so that's the outline of my talk. So we are going to look at, following this framework where the summary statistics are concentrating, look at the behavior of the ABC posterior distribution and see whether we can learn theta, even though we have lost quite a lot of information, and see how much it's affected by epsilon and the rate of concentration. And so not only are we looking at consistency, but also convergence rates. And then we want to be a little more precise, and by assuming a little more, which is asymptotic shapes, asymptotic limiting distribution of this eta z, we are going to have also a description of the asymptotic shape of the ABC posterior distribution. The question is, do we have Bernstein transmisses or not, to some extent? And then also, like if you take the typical point estimator from a Bayesian point of view, which is a posterior mean, what's the behavior of the ABC posterior mean? And all these three results I will describe in detail are going to be in the case where I'm assuming that I'm in the right model. To some extent, I'm going to say what it means. But then we're going to move to the case what happens when you have misspecified models. And then you have really weird behavior that can take place, and that's what I'm going to describe afterwards. So the asymptotic framework. So now you have y that's indexed by n because you have some information that's going to go to infinity. And we're going to have assume that the threshold is small. And what does it mean to be small? It means I'm going to assume that epsilon n goes to 0 at some rate when n goes to infinity. So I have a parametric model. So the dimension of my parameter is fixed. And I'm assuming concentration in the sense that for all theta, I assume that there is a function of theta around which my eta z is going to concentrate. Okay, in other words, eta z minus b theta is a little o of 1 under p theta. And what I want to see is under which condition, typically, do we have ABC posterior consistency. What it means is that can we learn theta naught? In other words, is the ABC posterior going to concentrate around theta naught as n goes to infinity? Although we have made quite a lot of approximation throughout the way. And now I want to be a little more precise. I would like to have a good upper bound on delta here. So I'm going to assume that I'm looking at shrinking neighborhood around theta naught at the rate delta n. And delta n is going to 0 fast, but not so fast, because I want to make sure that the posterior concentration rate of this posterior mass of these shrinking neighborhoods goes to 1 as n goes to infinity. And that's called the posterior concentration rate. But here is the ABC posterior concentration rate, because I'm looking at the output of my algorithm. And so that's the first theorem for posterior concentration rate. Yes?
So can you come back to the previous slide? I'm just a little confused by the order of quantifiers, so the concentration of eta of z. Do you want that for each theta there exists a b of theta, or you want to keep that for which this thing works for all theta?
No, I'm assuming that for each theta, my eta z, if I'm looking at a z from p theta, then eta z is close to b theta.
But can I take
it's not uniform. I'm just looking for all each theta as n goes to infinity, eta z goes to b theta. So for instance, if eta z is a sample mean of some function, then it will converge to the true expectation under p theta. And that's a typical example.
The p of theta is one function, right?
Yeah, it's one.
So this exists.
So for all theta, there exists a b theta.
All theta twice. All theta and then all theta after.
Yes, there is a bit. Just in case you miss the first one, there are two b theta, there are for all theta. So that's what you're confused. So what I want to make sure is, so forget about the four theta.
Thing, right? So they don't mean the same thing. So tell me which one I should remove.
Yeah, well, yes, they do mean the same thing. For what you want to know is what I'm here. You have a p theta, okay? So if z follows p theta, and theta is something, then eta z is going to be close to b theta.
Okay.
So but the b theta is not the same for all theta. The b depends on theta. So for instance, if eta z is an empirical mean, then it's going to converge to the true expectation, which depends on the parameter that drives the data. That's all I'm saying essentially. Okay, is that clear for everyone? So you want to so essentially that's what I meant when I said that the summary statistic concentrates. They concentrate on something that depends on the parameter, so that you can learn the parameter. Otherwise, if it doesn't depend on the parameter, you're not learning anything. Yes.
Yes. What about y? So here this holds
Yes.
for all y or without probability.
So
y.
So you have, because I'm in this first part of the talk, I'm assuming that my y comes from the p theta naught. It's part of the story. So eta y.
So when you say consistency, this thing, the quantity on the left-hand side is a random variable.
Exactly. Yes, of course. Yeah, because this is a p theta here.
The one in the next line, the next equation, that quantity is a random variable.
It is because yeah.
Right. So this is equal to okay.
It's a 1 plus a little op, and p is a p0. It depends. Is a true p0 for the true observations. Yeah, we are Bayesian. So you're going to bear with me, and you're all Bayesian for 3/4 of an hour. And so, so you have two different randomness. One is the theta, which is because you're Bayesian, and the other one is the usual randomness, which is the data. And here it's even more confusing because you're sampling new z's, and so everything is random all the time. So, so that's the point. Now the point is to find what's delta n, and delta n is going to depend on epsilon n, and also at which rate my summary statistics are going to concentrate on around this b theta when theta is close to theta naught. And so that's why I'm going to quantify my assumptions. So the first assumption is that you want to to say that the eta z converges to p theta, to b theta around under p theta at some rate. I'm writing it as if I was looking at some kind of homoscedastic rate, but you can generalize. So like here, so this is the rate of concentration. So typically think about 1 over square root of n. So sigma n is like typically 1 over square root of n. And so what I'm describing here is just a tail probability. So you're just describing the departure from eta z to b theta. And here I'm writing it as if I had a polynomial departure, the decay, but you could have exponential decay as well. So if you have some kind of control on the decay, on the departure between eta z and b theta, and then if your prior distribution has a density typically which is absolutely continuous with respect to Lebesgue measure, and you have some continuity on b theta, then what you know is the prior mass on neighborhoods of the true theta naught is going to be of order u to the power something when u is the radius of your ball. So this is the two types of conditions that you need, and under these two types of conditions, then you can control, you have an upper bound on the posterior concentration rate, which is the threshold, plus something which is like sigma n with a penalty, and the penalty depends on how fast you can decay here. Okay? So if you have an exponential decay here, so if you have, for instance, if eta z has exponential moments, now you'll have a log n penalty here. If you have only polynomial moments, then you have a polynomial decay here, so you're losing something, and the question is, really, are we losing something here, or do we have just the maximum between epsilon and sigma n, which is sort of the natural intuition that you would get? That you get either the threshold if the threshold is large, or you get the concentration of eta z if the concentration is larger. That's the intuition, and actually that's going to be the next slide. And so here, because of course eta z is learning b theta, this concentration is on b theta. But what you're interested about is theta. And so if you know, and that's not always easy to prove, if you know that you have a one-to-one function, so the function to theta goes to, which has theta associates b theta is invertible, and you have some kind of Hölder kind of bond like that for the inverse, then you get from a rate on b theta to a rate on theta. That's like a trivial step here. But because really what you're learning is b theta. You're not learning anything else because eta z is concentrating on b theta. And so now, can we be more precise than just this upper bound? That's what I'm going to talk about afterwards. But before talking about that, I'm going to explain where this quantity comes from. Okay? So as I said before, if we, instead of polynomial decay, you had an exponential decay, like for instance, if you have exponential moments for your eta z, then the rate becomes epsilon n plus sigma n times some log penalty. So it's not so bad, but it's a bit, it seems to be a bit artificial. So that's what I said before. One key thing in this proof is that the proof is actually extremely simple. And it's extremely simple if you take a special route. And because if you remember, the incentive of doing the algorithm was to say that if you look at the probability that eta z minus eta y is small, divided by the radius, then it's equivalent, it's approximately equal to the likelihood. If you want to control that and say the difference is small and so everything goes fine, then you're going to the wrong route and you have extremely strong conditions to prove what you want to prove. What you really should work with is this object. And actually I'm going to write it on the board, if I can. So what you're interested about, so the algorithm is really talking about something like that. And so what you're interested about is controlling directly eta z minus eta y less than epsilon divided by the same thing but on the whole space. So to have a proof that requires very small, very weak assumptions, you really have to work on this object. Because this object is actually much nicer than the likelihood, because it's much more well behaved. It's bounded and everything, it's bounded by 1. And using this sort of fact, you can get really precise results with very few assumptions. So that was sort of a key point in the proof. And then, well, I'm going to skip that. So, but all the results here assume that I am in a way specified case. In other words, that my eta y converges to some b naught, and b naught can be corresponding to some b theta naught. So that's what you need. Okay. So as I said, it's a very simple proof, and it goes that way. So what you're interested about is this ABC posterior. So you want to prove that the ABC posterior of b theta minus b theta naught greater than delta n goes to 0. And so this is a ratio of two things, an integral over this set divided by the integral over the whole set. And now what you're going to do is, on this set, you're going to bound from above this quantity. And on the very small neighborhood on theta naught, you're going to bound from below this quantity. And so to bound from above this quantity, there is a very simple remark that says that because eta y minus b theta naught is of order sigma n, eta z minus eta y is of order sigma n, and so if I take a threshold which is much larger than sigma n, and I'm going to win somehow. And so in other words, so this is much smaller than sigma n, and so to have eta y minus eta z less than epsilon n, over the set where b theta minus b theta naught is greater than delta n implies that eta z minus b theta is greater than delta n minus cis. So if this is much larger than that, then this probability is going to be very small. And that's how it goes. So it's a very simple proof. There is no high techniques there. And for the denominator is the same story. So now, as I said before, looking at that is a bit too weak a result and you don't know much. So what you want is really getting a much more refined analysis, because we are in a parametric framework, essentially. And so we want to get a shape of the asymptotic ABC posterior, whether it's going to be asymptotically normal or not. Can we say something about it? And then you have something which is quite funny that takes place, is that it will depend on how epsilon n behaves compared to sigma n. Epsilon n is the threshold, sigma n is the concentration rate. And so what happens is that if epsilon n is much larger than the sigma n, so if the threshold is much larger than the concentration rate, then the posterior distribution is going to have an unusual limiting behavior. It's not going to be driven by the eta z. It's going to be a uniform asymptotically. If a sigma n has the same order of epsilon n, then you have a perturbated Gaussian or something related to that. And if epsilon n is very small, then you have the usual Gaussian limit. So you have this sort of three regimes, and I'm going to describe a little more what I mean by that. So I'm assuming a Gaussian limit for the. So I need to assume a little more. So not only am I saying that eta z is going to concentrate around b theta under p theta, but actually I have a limiting distribution. For instance, it's asymptotically Gaussian. I've written it as asymptotically Gaussian, but you couldn't replace it by something else here. Let's say q. Okay, so I'm assuming that for all theta in the neighborhood of theta naught, I have this asymptotic distribution, and there is a contiguity between the sigma n of theta. So essentially the rate is the same when theta is close to theta naught. And I'm assuming also the same thing as before, so I have regularity of my link function, b theta to theta, and the inverse, oops, yes. So So under these two types of conditions plus the kind of conditions I had at the beginning, then I can describe perfectly what happens. And so as I said, if epsilon n is much larger than the concentration rate of eta z, then the ABC posterior is going to be to converge to a uniform random variable, uniform distribution. And the radius of the set on which the uniform is the random variable is uniform is of order 1 over epsilon is of order epsilon n. Sorry. So you have this sort of asymptotic distribution, whatever the limiting distribution of this object.
Uniform on what?
So it's on theta. So epsilon n, theta minus theta. Huh?
Theta is bounded.
So, but it's no, theta has it can be. It doesn't have to be on the compact.
The uniform distribution.
But so if you this is an ellipse B naught typically. So it's like a ball with radius 1. So here it's a 1. Huh? So you're looking at this radius, and here what it says is that asymptotically the posterior distribution of theta is a uniform distribution with mean theta naught and radius epsilon n. Okay, and it's because you're concentrating.
It like this? Is the limiting random variable a random variable, or what is it?
Yeah, of course it's a random variable. It's like the Bernstein-von Mises, but you don't have a Gaussian at the limit. You have a uniform.
Yeah, but the normal distribution lives on Euclidean space, whereas.
Yeah, but so here what it means is that with probability going to 1, you're going to live on a compact space.
And what is that compact space? That's
it's a compact space of radius epsilon n.
The limit cannot depend on n.
Well, yes, of course, because it depends on n. Because oops, sorry, it depends on n. It's a bit the same. Like when you have Bernstein-von Mises, you say under the posterior distribution, theta minus theta naught, theta hat. I mean, it doesn't matter here. It goes under the posterior distribution to a normal 0 sigma squared. Okay. So here the square root of n has the same role as my 1 over epsilon n. If you think about it, it's the same. So, but instead of having a Gaussian density, you're having a uniform on a ball with radius 1.
Radius 1.
Yeah, because B0 has radius 1, and so, but if you, the epsilon n is there. So this is the rule, this plays the rule of square root of n.
Okay, so if it's a unit ball where the uniform distribution is supported.
Yeah, exactly. It's a unit ball for this rescaled and recentered variable. But for theta, it corresponds to being centered on theta naught with radius epsilon n, essentially. Is that clear? Okay. But it's completely an unusual. It is a completely unusual asymptotic behavior. Now, if epsilon n and sigma n have the same kind of order, then you get a more traditional kind of recentering. So the recentering of your posterior distribution is not going to be on theta naught, but it's going to be on theta naught plus z naught divided by square root of n, essentially, if you think about it, where z naught is this thing. So you can think about z naught as a score, essentially. And the limiting is not going to be exactly Gaussian, but it's a perturbated Gaussian if you have a Gaussian limit for eta z or eta y. Now, if epsilon n is much smaller than sigma n, then you have a Bernstein-von Mises result in the sense that the posterior distribution of this recentered and rescaled theta is normal with mean 0 and variance identity, and the rescaling is this quantity, which is exactly the variance of the recentering point. So you have what I call a Bernstein-von Mises result in this case. So what's surprising is this epsilon n uniform ball at the end of in the first regime, because it's not at all what we expected. But when you think about it, it's not surprising. It's quite easy to understand, and it comes from going back to that. Now, if you are in the regime where eta z epsilon n is much larger than sigma n, eta z is equal to b theta naught plus a big O of sigma n. Eta y, b theta plus a big O of sigma n. Eta y is b theta naught plus a big O of sigma n. So this guy here, it's like b theta naught minus b theta plus a big O of sigma n, big O p of sigma n. Okay? And so when you're interested to see whether it's smaller than epsilon n, because epsilon n is much larger than sigma n, it's as if essentially you're looking whether b theta naught minus b theta is smaller than epsilon n or not. Essentially, so that's like a heuristic argument. You can make it more precise, but that's exactly what happened. And so this probability is just replaced by the indicatrix that b theta naught minus b theta is less than epsilon n. And so that's why you have a uniform limit at the end of the day, and the behavior of eta z doesn't tell you anything, somehow. So you do still have concentration around theta naught, but at the rate epsilon n. And so that, as I said, that T naught is, you can look at it as a score with this ABC a posterior distribution. And why is that so? It's because that T naught is exactly the score if you were looking at the likelihood based on eta y. So if you had the model where the observation is not y but eta y, your summary statistic, and you had the likelihood for this model, then the score function for this one will be exactly that T naught. So that's why I call it the score, asymptotic score. So now the question is, so this is the shape of the posterior distribution, and I have this sort of three regimes. If epsilon n is, it's only if epsilon n is much smaller than sigma n that I get asymptotic normality and Burschen-Von-Mises results. But can we do something better if we're looking only at point estimators? So if I look at the posterior mean, what can I say? And this was sort of this idea of looking at that was from a paper by Fernhead and Lee, and we didn't where they had a different set of conditions, and so we wanted to understand better what it meant, and so we did the proof again in our context. So and then you have a funny phenomenon that takes place if the dimension of theta is the same as the dimension of your summary statistics. Typically, the dimension of the summary statistic is larger, but if it's the same, then you can exactly write down an expansion of the posterior ABC mean, the posterior mean under the ABC, minus theta naught. And then you have the score again, so you have the usual classical framework if you were to observe eta y instead of y, plus a bias term here, which depends on epsilon n, so depends on the threshold. And these functions ht are deterministic, so it's really a bias term plus a little o of these two terms. And so here what happens is that you can get the posterior mean can be asymptotically efficient even when epsilon n is larger than sigma n, but if epsilon n squared is still a small o of sigma n. So you have an intermediate regime where the posterior doesn't behave really nicely, but the posterior mean behaves nicely. They have the right of behavior. Another result that's interesting from that, which was a bit surprising as well, is that actually, so there was a paper by Fernhead and Prangel that said that so somehow the best summary statistic that you could take is a posterior mean. But of course, if you could take it, then you wouldn't use the algorithm because you would be able to compute the posterior mean. And so they had this sort of two ways algorithms, two iteration algorithms. They took an ABC to compute an ABC posterior mean within another ABC, and then they use this ABC posterior mean as a new summary statistics. And what it says is that actually if you do that, in the asymptotic regime, you're not learning anything, and you could just do it one way, you get the same information on both sides. And so it's there, you don't learn more by doing the second round of ABC of the algorithms. Because what you learn is what you put in the summary statistics. And so you have a first set of summary statistics, you're learning what you put from them, so you have the asymptotic distribution from them, and you'll never learn more than that. Even if you reuse them afterwards, what you get is the asymptotic distribution of the first summary statistics, and you cannot do better than that anyway. So that was a sort of the surprising result there. And now you have another surprise, which is in the usual framework where the dimension of eta is greater than the dimension of theta, so the dimension of B is going to be greater than the dimension of theta, then you're losing something. So there is a loss of efficiency in the sense that even to fourth order, so even if epsilon n squared is smaller than sigma n, then the first order is not the efficient score, but it's something which has a variance which is larger. The efficient score would be this one, and that's what you get. And so there is a loss of efficiency when you take a too large summary statistics. So you don't want to do that, but you cannot always do that. I suppose I have 10 minutes again, thank you. And so the same story, so there is no point, at least in the asymptotic regime, to do a two-round algorithms by doing this sort of Prangle and Fernhead story. So now the question is where does the dimension of your eta kicks in the algorithms? Because as I said at the beginning, there is a trade-off between the dimension of eta, which has to be small enough so that you don't reject all the time, and enough precision in your data, so enough concentration somehow. So an efficient score, a good score. And so here the dimension of eta hasn't played any role for the moment. We are not paying any price for the dimension of eta. And the dimension of eta plays a role only when you look at the probability of accepting these thetas when you simulate them. And that you can look at it when you look at alpha n, the probability of accepting new data from your prior, essentially. And that's how you see the dimension of eta coming in. But actually, it doesn't play such a role. You're not killed by the dimension. And the reason, and in particular, if epsilon n is much larger than sigma n, or is larger than sigma n, then the probability of accepting eta when you have a radius epsilon n here is of order epsilon n to the power k, where k is the dimension of theta, not the dimension of eta. So if you have concentration and you have large summary statistics, you're not killed by the dimension of the summary statistics. And the reason why you're not killed is because the summary statistics concentrate. And so essentially, you're living in a tube around a k-dimensional space. And so it's as if you have a dimension of order k, because the tube is small around your k-dimensional space somehow. And so that's why you're not killed. And if epsilon n is much smaller, then you're paying a price, but the price you're paying is really only to the ratio epsilon n over sigma n to the power k1 minus k, where k1 is the dimension of eta, and k is the dimension of theta. So that's the good news, is the fact that if you have concentrating summary statistics, then you're not paying too much of a price. So now I'm going to just skip quickly about this misspecification, and I'm going to show you a graph and tell you what kind of results we have obtained in this case, because I don't have much time. I need to change the slide, because it's a bit crappy. This one. This is it. So this is the same graph. So here what we've plotted is the posterior mean, and so the true value is 1 here. So the posterior mean in the case where we are misspecified. So the true value is 1, but so we were it's really a baby example where we were simulating y that are normal 1, 1. And we used as a model a normal 1 sigma, and here sigma is increasing. So here you have 0.5. This is the true value of sigma, and then you're getting away from the true value. So the red line is the ABC. The red line is the ABC algorithm, the usual one I described, and the black line and the blue lines are variants that are supposed to be better, that are supposed to be much more efficient. And so this is when you use the indicatrix, which is by another kernel for the acceptance story. And this is when you do a post-processing here with using a regression model. And what you see is that actually when you misspecify, the ABC is still not too bad in terms of point estimator. But if you do the variants that are supposed to be much better, you're completely off. You can be really bad. So the variants are not at all robust to model misspecification. So here you have to be, because you have all these epsilon n story, model misspecification doesn't mean that it is not so bad in the sense that you can be model misspecified in the usual sense without ABC being ABC model misspecified in this sense. And the reason is that you're going to be misspecified only if the B naught, which is sort of the value around which eta y is concentrating under the P naught. So this is your true data, this is your true value, true distribution. Eta y is concentrating around B naught, and you are going to be misspecified if the infimum between B of theta and B naught here is strictly positive. So it doesn't. So you have a lot of models for which you're not well specified, but still the infimum of this distance is equal to 0. And so the ABC distribution is going to be fine, and every variance is going to behave well. But if you cannot reach a b theta by b naught by this b theta, then you are misspecified in the ABC sense. So there is robustness because you are using an approximate model and an approximate algorithm, but when you are not even well specified in this framework, then you can be in real trouble. And I'm going to explain a little more if I have 1 minute, a couple of minutes, what happens in the for the asymptotic distribution. Because you have something, again, a bit weird that happens. Pom L, no? Control L. Yeah. And so we can prove the same theory. So we can look at posterior concentration rates around the projection. In other words, the smallest, the one that attains the this infimum here. And but what I'm going to describe is not so much the posterior concentration, is really the limiting shape, so the asymptotic distribution of the posterior distribution. Well, so whether do we have the same story as we had before with uniform limits for epsilon n large, the sort of perturbated Gaussian for epsilon n like sigma n, or Gaussian distribution for epsilon n smaller. And you have something even more different here. So now sigma n is 1 over square root of n to make it simpler. And what happens is that if epsilon n, so if your threshold goes to 0, you don't know what's going to happen. Probably you're not convergent to anything. So you don't want to have an epsilon n that small. And the reason is that anyway, you cannot, this b theta minus b naught is strictly positive. And so when you're looking at eta z minus eta y, you cannot be smaller than that guy. And so the key story is whether you are of this order or whether you are a bit too large or a bit too small. Okay, and so what happens is that if you are, if epsilon n is equal to b theta star minus b naught plus a little o of 1 over square root of n, then you have an asymptotic non-standard distribution at the rate which is not the square root of n rate, but it's n to the power 1 over 4. So you have a completely non-standard asymptotic in this case, with a non-standard limit and a non-standard rate. So it's a bit weird, but it's because you are in a weird setup. Huh? And you get the uniform story again if epsilon n is large. So you have still for this part, it doesn't change. And when epsilon n is too small, which is here, then we don't know what happens. So it's an ongoing work, and we haven't described yet this context. We're not even sure we are converging, actually, in this case. So maybe the posterior, the ABC posterior in the misspecified case is not converging. In practice, yes?
Just for my sake, so what assumption do you make on this slide, for example, on B, so that you can go from closeness of B theta star to B theta naught to closeness of theta to...
So the kind of assumption that you're making here, because, so here I wrote like that, but otherwise I could write B theta and B theta star, okay? But so here I've written it like that, so I'm assuming that, again, the same as before, this is invertible, and the reverse is Lipschitz. Then you're not losing any rate or anything, okay? So this is under this assumption. Yeah, it's a good point. Actually, this is under this assumption. H star is a given matrix that depends on theta star, and it doesn't depend on theta at all. It's only it's a second derivative of b theta minus b theta star, the square norm. So it's something that doesn't depend on anything else than that. So it's really a non-standard asymptotic, and I mean that's the math. Huh? That's what we can say about it. And so, but what's nice is that you can have a diagnostic. And that's the second plot. I'm not going to explain the diagnostic, I'm just going to show you the plot. It's easier, actually. And then that's it. So the diagnostic is that somehow if you're saved, if you do the ABC, and so in practice what people do is they are not going to fix the epsilon n, because they don't know how to fix the epsilon n in the threshold, but what they do is they simulate a lot of thetas, a lot of z, and then they're looking at the quantile of the distance between eta z minus eta y. And they're taking the alpha n quantile, the empirical quantile, and so it's not epsilon n that you're fixing, but it's the quantile alpha n, the probability of accepting, essentially. And so if you take epsilon n, alpha n small, but not too small, then you are in the right regime for the asymptotic limit, even in the misspecified case. So you have a weird asymptotic, but still some asymptotics, let's say. So you're safe then. And so, but what's funny is that if you can plot that in practice, if you plot the function of alpha n in terms of epsilon n, then you see that if you have a small discrepancy between the models, then the red curve starts becoming a bit different from the black curve, which is alpha n, what it's supposed to be. And as the discrepancy between the models increases, you can see like a dip here. And the deeper, the larger the distance between your B theta and B theta star and B naught. So that gives you a, so if you see something like that, then you know that you are in this context. So that can be like a diagnosis for something going wrong in the approach, in the model typically. And just now wrap up. Just a summary and it's done. Sorry. So just to wrap up the story, so we have a characterization of the asymptotic posterior distribution under the ABC, which is an approximate algorithm. You have different regimes, and with non-standard asymptotics for some of them, you can get efficiency in a sense, and when I say efficiency, it's the usual efficiency, but if you were to observe eta y instead of observing a y. So there is a lot of information by the fact that you replace y by eta y. If you were to observe eta y and have a model on eta y, then you would have an efficiency story. And you can be efficient in this model using an ABC algorithm with epsilon n small. But epsilon n doesn't have to be too small, and we know how to control that. But you really have surprising behavior under misspecification. That's it. Thank you.
I think we can have one question. Or two.
So in the uniform limit, sorry.
So, assume that you have a regular model
Yes.
for which the maximum likelihood is intractable, but you know that it is efficient.
Yes.
And then you suggest some method which is randomized. As I understand, you have some choice of parameters epsilon n.
Yes.
For this method.
Yes.
When you achieve the efficiency.
Yes.
So under which assumption?
So the kind of assumptions that you need, so the efficiency, again, it's efficiency with respect to this kind of observation. So you have to, because you're replacing y by eta y, so the real model that you're considering is a distribution of eta y, okay? And then the assumption that you need to have is that essentially when epsilon, so I'm going to assume that the d is equal to 1 to make it simple. So this minus b theta, when theta is close to theta naught, this less than epsilon, less than h over h goes to the density of eta y. But you don't have a uniform control or anything, you just need that kind of assumption. Because you are in the
efficiency in the classical sense, you say.
Yeah, in a sense, I'm thinking at the same time. So you don't have efficiency in the classical sense, no, you're right. But in the sense that somehow, in the limiting sense, yes, because somehow this, so this is Gaussian, this is a Gaussian distribution, minus b theta squared times n divided by some v like that. So this is it, and somehow, if you were to look at this model, okay, and you wanted to estimate theta with a 1-to-1, exactly the variance of the maximum likelihood estimator would be, imagine b theta equals theta, just to make it simple, would be v. And then that's exactly what you get from the Bayesian estimator. So in this model, in the limiting model, then that's exactly what you get. And so now whether it corresponds to efficiency without looking at this aspect, but looking directly at this function, as the non-limiting values, I haven't looked. So I haven't looked at the real starting point of the model. But if you think about it as a limiting model, then you get the limiting efficiency. So it should be the same. That's my guess. But I haven't proved it formally. Does it make sense what I'm saying?
Okay, so the other question will be offline, I understood. So let's thank